Hello, welcome back. So, where are we? We have derived the wave equation of the electromagnetic radiation, the wave equation of light, the second order derivative in time and space. We made an assumption that our wave function could look like the following. The electric field component is E naught times sinus kx minus omega t. We did solve the wave equation in the following. We plugged in the wave equation into the wave function into the wave equation. We did build the second derivatives in time and space. We immediately realized, yes, hooray, it works. And as a second result, we got the speed of light out of that expression. Actually, C naught is 1 divided by epsilon naught mu naught square root. This is what Maxwell had already figured out back 1872. And from that result, he concluded that light is nothing else than an electromagnetic wave. What amazes me is that you can determine the speed of light with a simple tabletop experiment. If you have a non-magnetic material, you just need to determine the electric susceptibility, and that can be done in a simple plate capacitor type tabletop experiment, and you can, from that result, directly calculate the speed of light. So this is what really amazes me in person. Electric field traveling in space, electric field traveling in time. Now, some further properties of light. One important property is the electric field and the magnetic field are always perpendicular to each other. E is perpendicular to B, always, and on top, perpendicular to the propagation direction, or in our terms, the wave vector. Though these three are always perpendicular to each other. Another important property of light is the electric field and the magnetic field, and that I'll try to add that here in that figure. Magnetic field, sorry, that should go right through that same node here. Magnetic field is always perpendicular to the electric field, and the starting point, the nodes are always identical. Just to make sure, the magnetic field would here pointing out of the blackboard. E field is perpendicular to the B field, and all the two are perpendicular to the propagation direction of light, and that's the wave vector k. The starting points are always identical, so you could also call it the electric and the magnetic field are always in phase to each other. Last but not least, we had our equation number 1 and 2 in the very beginning of the summary, derived from the Maxwell equation, Faraday's law, and Ampere law. If we now plug the time derivative of the electric field and the space derivative of the magnetic field into equation number 2, you would directly get a relation between both amplitudes, namely E naught, the electric field, is speed of light times B naught. That's the relation between both amplitudes. light is an electromagnetic wave. It always comes to electric field and magnetic field all together. They're both coupled to each other. Electric and magnetic field are perpendicular to each other, and the ratio between both amplitudes is the speed of light. So this brings me to the next chapter, energy transport. Does light carry energy? I think the answer is pretty simple. If you go to Coogee Beach, not in our days with the virus, but in general, you get immediately a sunburn. So yes, the answer is clear. Light carries energy. And the keyword for that is the Poynting vector. Chapter 2.12, energy transport and the Poynting vector. So when I was a student, I was asking myself all the time, why is that vector pointing at something? No, that's not true. It's a name of a scientist, John Henry Poynting. (1852 to 1914, and he was a professor in Birmingham. The Poynting vector is defined as follows. S is 1 over mu naught E cross B. The electric field and the magnetic field are already permanent, all the time perpendicular to each other. The cross product here underlines that even further. What are the units? S is defined as energy per time and area, a certain area which is illuminated by light. Or you could call it also power by area. That's the unit. What's the direction? A vector has a direction. E cross B I just summarized that the electric field and the magnetic fields always perpendicular to each other and perpendicular to the propagation direction of light. So that gives you the propagation direction of light. Or, simply spoken, our k vector. It's in the direction of our wave vector k. That's the direction of the traveling wave. So, let's talk about the units of S in a bit more detail. So the magnitude of S is 1 divided by mu naught E times B. Let's skip the vector symbol here, just the absolute magnitude. And we also have learned that the relation between the E field and the B field is speed of light, where the speed of light was 1 divided by square root epsilon naught mu naught. So, if we use that, we can actually rewrite the expression as follows. 1 divided by E squared. And now what do we have to put here? Let's combine these two prefactors and we get speed of light times mu naught. We can also express that in terms of B. And now we get speed of light divided by mu naught. That's another way how we can express the magnitude of the Poynting vector, the power of light, the light intensity. And here's a highly important message already. The power of light, later on for simplicity we might call it intensity of light, is directly proportional to the electric field squared. That's a highly important result here. So two more considerations here. The energy density is actually the electric plus the magnetic field part. U total and if we would define it as energy density, both together would add up to that expression, which means the electric density would be 1/2 of that expression. And the magnetic would be 1/2 B times H. Here I used one further definition already, the E field and the B field. You had that in the previous lecture of Tim Duty. The D displacement, electric displacement, is actually epsilon r times E. That's if you are in a certain medium. Or we can rewrite that as 1/2 epsilon r times E squared. The same holds for the magnetic field. That's the energy density if we combine both electric and magnetic field together. Another consideration, what's the average? Finally, the intensity is the average of the Poynting vector. So, and that's in our straightforward explanation here, 1 over speed of light times mu naught times E squared averaged. Well, remember our E field was a wave. Now we need the square of that expression. Here in space, and sine squared actually looks like the following. This is sine squared of kx. And here is our E naught squared. Time average, two options. You can integrate from 0 to infinity, or you simply have a closer look at that view graph, and you realize that the upper parts and lower parts here are identical to each other. So you could simply flop that section into here, flip it around, and you realize that the area, filled area, is just 1/2. That's a simple approach to solve that integral, this time average. And if you do so, you get directly that the intensity, or the averaged one, is 1/2 1 over c mu naught times E naught squared. This is the averaged Poynting vector, or our intensity. Other approach to the same expression is you take the RMS. That's the root mean squared value for the average. And here that's E naught divided by square root of 2. And if you use that expression and plug it in, you get the same. The intensity is the averaged Poynting vector is 1 over c naught mu naught E root mean square. And this is the same expression, 1/2 1 over c naught mu naught E naught squared. The same story, of course, for the magnetic field, where you get 1/2 c naught mu naught over B naught squared. That's the expression for the Poynting vector, or in simple words, the expression for intensity of light. Thank you very much. So that's this chapter, Poynting vector.